So we are recording now, and there's a garbage truck outside, so hopefully you're not hearing that noise. So let's turn up our volume just a little bit here. Okay, so today, I don't really have any special announcements other than just we will have a new lab coming up this week. So our practice quiz today is going to focus entirely on some of the background information you will need for this upcoming lab. So let's all go ahead and open up our practice quiz. If you go to Canvas, you should see practice quiz Monday 10/12. And I made a little note, like, don't feel bad if you can't quite keep up with everything. We're just going to sort of walk through some of the MATLAB coding that you will need. And I guess I could post, I don't want to necessarily post what I put on because I want you to write the code yourself because you're going to have to kind of turn this in for your lab. So I'll just say follow along a bit. And I've got sort of divided feelings about whether or not to post the result or not because you're going to use this in your lab. And should I just give this to you or should you kind of have to write it yourself? So I'm inclined to say you'll have to sort of write these yourself as we go, because there's a few different variations we'll be doing with this. So let's go ahead. I'm going to share my screen. So this is our practice quiz for the day. And we're talking about the microstrip transmission line. So I just give some basic values for a typical printed circuit board. We'll have a thickness of about 1.6 millimeters. That's actually the value of your copper clad laminate. And I was looking around on PCB manufacturers' websites, and 1.5 millimeters, 1.6 is a pretty standard thickness for a cheap 2-layer board. And the dielectric is called FR4. So it's a generic designator for some flame retardant plexiglass, something epoxy resin, whatever this magic material is. So the FR stands for flame retardant, and the 4, I guess, is number 4. But it's just the common material that is used to make printed circuit boards. And the dielectric constant tends to vary a bit. This is going to be part of your lab, is to actually measure the dielectric constant on your board a bit. But it tends to vary between 4 and 5-ish, 4.2 to 5.2. From what I could tell when I went through the lab, it was about 4.2 to 4.4. But I saw a lot of websites saying it could get as high as 5.2. And there's going to be like a frequency dependence to this thing as well. So you have to kind of keep that in mind. So depending on the exact recipe of whatever manufacturer is using to put this stuff together, you get kind of a range on that. And also, fun fact, the minimum trace width on a printed circuit board is 6 mils for some manufacturers, 5 to 6 mils. So that's like a little over 1/10 of a millimeter, which feels about right. So I just had, give me one sec, here we are. So I'm going over to the desktop camera here. So here, I'll stop screen sharing. And I'm gonna go to my desktop camera here. So here is actually an Arduino. And let's see if we can look really, really close. I don't know if you can quite, there we go. You can see the little copper traces there if you get the light just right. So those little bright streaks radiating off of the chip, those are little copper traces. And so you can see they can get pretty tiny. So I would say that's probably about 1/2 millimeter on that right there. So they can get very, very small. So let's go back to the screen share. So I just did a little digging. So about 6 mil is kind of the smallest that they can go, but you can kind of make it arbitrarily large. If you ever do any printed circuit board manufacturing, you can kind of just specify that thickness as however thick you want. So what we're going to do is we're going to use the expressions in Posar to create a plot of the characteristic impedance as a function of that trace thickness, and maybe do a few variations on the dielectric constant as well. So just a quick overview. Here we go. So let's go back to stop sharing. So I'm going to show you. So here is the relevant section in POSAR. So I'm on page 148. So if you watched the lecture, remember I said there are no closed form solutions for the electric or magnetic fields around this geometry, which is kind of interesting. I have sort of mixed feelings about how this is introduced, because we spent the last 2 to 3 weeks where we were solving Maxwell's equations exactly, getting these nice crisp solutions, and they were mathematically hectic, but they were very informative, and they tell you basically everything you need to know about the electric and magnetic fields inside these waveguides, and you get these nice profiles and everything. So it's, here's an exact solution, here's some more exact solutions, here's some various wacky stuff, and then finally at the end, they even do the strip line, which is 2 parallel conductors with a positive trace inside. And they even do kind of a decent mathematical derivation of this. It's not perfect, it's not exact, because they make a few assumptions that aren't the best. But it is, a pretty good, valiant attempt at getting a nice closed form solution for this thing. And then finally we get to the microstrip line, and they just throw up their hands. Like, nope, we're not even gonna try to solve the fields in this thing. And so I'm not sure if it's totally out of place or if this is the perfect place to introduce it. But so we're going to close off this section by basically saying, here is yet another geometry. It's very common all throughout industry. Don't even think about trying to model this thing and solving the electric and magnetic fields around it, because it will be a horrible mathematical nightmare. Better men than you have tried and failed. So in principle, it can be done. If you get very careful with your boundary conditions and your matching, you could create a big, giant sort of infinite series of linear equations all matching these boundaries together. But it would be extremely nasty and complicated if you tried. I've thought about tackling this problem. I think if I had about a month to do nothing but beat myself on the math of this, I could probably do it, but it would not be pretty. But it would be cool to have like an actual MATLAB's function that would calculate this stuff with infinite precision. So to get around that, well, I looked briefly. These are references from the 70s that would actually make a good final project. If you want to dabble in these, you could get it probably from the library. So you look over here, some guy wrote a book, Designer's Guide to Microstrip Line. And then there's other microstrip lines and slot lines. So you notice it's 1977 and 1979. Somebody went through a lot of work to give us kind of some decent modeling for the microstrip. So it looks like all they did, I think they're books, so I can't just download a digital copy of anything. But from the description here, it looks like all they did was a bunch of numerical simulations, and then they just kind of figured out a way to do some kind of basic curve fit on all of these parameters. So the first thing you need is this, what's called an effective dielectric constant. So the idea is, they got a nice picture here. You imagine here is the actual microstrip where it's air up top and this dielectric slab in the middle here with your strip. And he says, there is some phase velocity associated with this arrangement. It will have a characteristic capacitance and a characteristic inductance, which will manifest as a phase velocity. And so what you can then do is hypothetically imagine filling the entire universe with some fictitious dielectric material like this to give you an equivalent phase velocity as this system here. So that's why it's called the effective dielectric constant. It will be something less than this value here, but it will be as if you filled the entire universe with that to give us a simple expression for our phase velocity. So they came up with, it's actually a pretty straightforward curve fit here. So you just do this little plug and chug here. And you notice it's a function of this, 1 over square root of your height divided by the width of your strip. Then once you have this effective dielectric constant, you can then plug it into this expression here to get your characteristic impedance. You notice this is pretty nasty as well. It's this giant piecewise function. So they have 2 regimes for a very thin width versus a thick width. So as the width gets very, very thin, you have to use this expression here. And then when it gets very thick, you have to use this nasty expression over here. So it looks worse than it is. because you can just stick this in the MATLAB and it'll crunch on it immediately. And all you have to accept is that there's a tiny bit of error in these expressions. They're approximate curve fits that kind of closely follow the numerical values they got. So they won't be exact, but they'll be pretty close. They're kind of good ballpark figures. If you want exact, you got to simulate it. But these are kind of a good, I guess you could say, back of the envelope way of figuring out your impedance based on the geometry. They also have this other expression here where suppose I know the impedance I want, what should this ratio over here be? And they do all this. And I decided like this isn't really worth it because you can just do a plot of this and then single out your width based on whatever characteristic impedance you have. So we'll kind of walk through that in class right now. So I'm going to go ahead and share my screen. So first things first, we just need to create a script and a function. So I'm going to go ahead and start by making a function, which I'm just going to say something like microstrip Z0. I already wrote one called microstrip impedance that I don't want to overlap with, but this is all we're going to do. So to create a function in MATLAB, first things first, let's start with the header here. Calculate the characteristic impedance of a microstrip line. So to create a function, the idea is it's a self-contained piece of code where you just give it some numbers, it applies a rule and spits out a result. So we're going to need our Z0, and we might as well return our effective dielectric constant while we're at it. So these are called the output arguments. I'm going to say microstrip Z0. All it needs is a width, a height, and a dielectric constant, E sub r. And then you can just put a little n here. So we're just going to look at the equations in the book. First things first, we got to calculate the effective dielectric constant. So hopefully you all have a MATLAB window open and you're following along a bit. So we'll just say, we can call it EE, or I'd say EPS sub E. I don't know any clean way to say epsilon sub E. We'll just go ahead and do that. So make a note here. See posar, actually we'll do this up here. It's also good when you're writing a script like this is to include references. We'll say posar page 148. So making mistakes or you come back to this a few years from now, you've got a nice reference to look forward here. So ER plus 1 over 2 plus ER minus 1. So as a general rule, the over 2 is fine, but sometimes it's a little neater to say 0.5 times, because now I can do my 1 over square root a little more neatly. And it's 1 plus 12 times D over W, just like that. And now, check W over D ratio. So you just say if W over D is less than or equal to 1. Oh, wait, yeah, sorry, I'm looking at the wrong expression there. We'll just say Z0 is equal to, we're just copying right out of the book here. I'll just bring my textbook over. So you say 60 divided by the square root of my effective dielectric constant. And it's times the natural log. So we do 8 times D over W plus W over 4 times D, like that. Otherwise, you get this other nasty equation over here. Z naught is equal to 120 times pi over square root of that times, and then you get this big nasty. So sometimes a good little trick is when you have a big ugly equation, split it up a bit. I'm going to say denominator is this thing, W over D plus 1.393 plus 0.667 times log of W over D plus 1.444, like that. And then I'm just going to say times 1 over that thing. So that, otherwise, if you don't do that sort of thing, you get these big equations that want to eventually fall off the edge of your code here. So it's a good practice sometimes to break up big complicated equations like that. I guess we don't need that guy there. There we go. So hopefully, if we've done everything correctly, this will work pretty well. So what we'll also want to be careful of is you could hypothetically feed this a bunch of vectors, and it won't like that the way this is set up here. I might give it a vector of W's or D's or epsilons. So a good way to check on that is just say if length of W is greater than 1, we'll just say error. Say something like scalars only, right? And you could, that's a good way to make sure you don't accidentally feed it bad inputs here. Like that. You don't necessarily have to add this in, but it's a good little dummy check there to keep you from accidentally feeding it bad input. So hopefully I've done everything here correctly. I've got one that I know is working, which we can look at later. But let's go ahead and run that. So this is the actual one I wrote before. So you see it's got the same code here. So if I made any mistakes, we can use the one that I know is working here. So let's go back now to our in class here. So let's start by create an array of, or let's see, define microstrip geometry. I'm going to say D is going to be 1.6 millimeters. And we'll start by just saying epsilon r is 4.2 dielectric constant. And then we're going to sweep over a bunch of different values of W. Do something like this. In space from 1 to 10, we'll do like 101 samples. So 1 to 10 millimeters like that. So what we're just going to do now, finally, create an array of empty characteristic impedances. Something like that. Now we're going to loop over this. So we'll just say colon. So you go back to your function. Like that. So this is why it's nice to create a function. So you notice we're just going to call that function. We're going to give it these values here. Oops, sorry, my microphone here was pointed the wrong way. Hope you could still hear me. And we'll just see if that runs. And yeah, it ran okay. So now we're just going to go ahead and plot our results. So plot W, function of Z naught. So there we go. So you should see something kind of like that. And so let's go ahead and mark this up while we're at it. X label, microstrip width, which is millimeters. We'll say characteristic impedance. like that. Or we can actually just say omega. There we go. So you can see as the strip gets thicker and thicker, the characteristic impedance goes down. And as it gets thinner and thinner, it wants to skyrocket up to infinity, which is kind of interesting. All right, and that is the kind of curve you should get. I've actually done some simulations to see how well that really agrees. So I can pull that up as well. So let me go find my lab here. There we go. So this is what I did some actual simulation to see how well it agrees. So if you take numerical methods, you can see how the simulations work. So you can see that that curve fit approximation actually isn't half bad. It agrees very strongly with the numerical simulations here. So that's very reassuring to see something like that, because it tells us that this approximation is actually pretty good. It's working very well. So it is a nice little reliable tool for designing a transmission line using a microstrip. So you can see, like, we didn't really solve Maxwell's equation. This is a purely empirically kind of derived formula that seems to give pretty decent results. So for example, I could say, all right, what thickness will I need in order to get a characteristic impedance of 50 ohms? So a nice simple thing to do that I like to do is we'll just go ahead and say, hold on, and I'm going to plot the following. I'm going to say 110, say 50-50, with a red like that. So there is 50 ohms, and you just have to figure out where they intersect here to see what your width needs to be. So if I zoom in, you see you need about 3.2-ish, 3.19, 3.2 millimeters will give you a characteristic impedance of 50 ohms. And in fact, if you do exactly 3.2, you can just sort of follow it along here. There's you'll get like 49 ohms if you do exactly 49.9 if you're exactly 3.2. So it's pretty stable there. All right, and so that's actually what I've got here, which you'll be using in your labs. So let's go back to the desktop here. Yeah. So this is my overhead camera. So that right there, I did by hand. You can see it's a little flimsy and sloppy, but it actually gave pretty decent results. It was something within a couple of ohms of 50 ohms there when I actually measured it. So I have a, here you go. So here's your ruler. The idea is, you can see, if you zoom way in, that's a little over 3 millimeters, just a smidge. Okay, so you won't be absolutely perfect when you do these by hand, but they'll actually be pretty forgiving from what I can tell. There's a little bit of wiggle room in terms of getting this stuff to work right. And you can see how there's a lot of like bends and nastiness in here, and they don't seem to hurt the actual behavior very much. It's pretty robust against that kind of, those little perturbations.
I'm sorry, on the very right side of the skinny strip, did you solder it on?
Oh, that there?
Uh-huh.
I attempted to solder one of these here and I botched it. So I just tore it off and then put it back over here on the left. So that's why there's a little blob of solder there.
Yeah, so I assume we don't need to solder it on?
So initially I set up the lab where you would have to solder it, but the problem is soldering back here is a nightmare. This copper plate is essentially a giant heat sink, and it's very, very difficult to get a good contact here. So Jackie actually came up with a good idea where you basically take a tiny little piece of this, and in fact, I can do a quick little demo for you right now. Let me just get out this right here. So in your kit, you should have a bunch of these little parts here. And I found that if you just take this, you kind of slide it on. Where do we go here? Get in there. You can actually just kind of press it, and it'll make a decent enough contact by pure friction if you just kind of slide it in there. Because you can see how everything's kind of touching. But it is a little loose. So Jackie also had a suggestion where what you'll do, just need some scissors here. if you find that you're having trouble getting a decent contact, you can take a little piece of your copper tape and just sort of like fold it in half, then do something like this where you slide it in underneath if you're not able to get a decent contact like that.
Oh. Okay, cool. Yeah, thanks. Just want to double check.
So this is actually a pretty good contact for me. I think I actually bent the inner conductor just a tiny bit. I think you can see, if you look very close, it has a slight upward bend. So this particular guy is actually making a good contact. Let me find another one. See if I can use this guy here. This might be a little bit looser now. Yeah, that one's a little bit looser. So one thing you can do, if you just bend that conductor a smidge, it'll make a decent contact. But if we try this, so this was Jackie's suggestion. There we go. So you see, I just smushed that in there. If I can get a decent contact. Oh, come on. Something like it. So you might struggle with this with your lab, but this is still better than having to solder it, I promise. So if you get that in there, there we go. Maybe something like that. There. So you see it's just kind of smushed in there by friction. And that contact is making contact there. I lost it. So you might have to do a little bit of trial and error to make yours work. But you can try and solder if you want. It won't be that hard to solder the top. It's the back side that you'll have the most trouble with here. So
did you use the oven on the back?
Did I use what?
Did you pop it in the oven to heat up the back plane before soldering?
No, I just cranked the iron up to full blast, and I just kind of held it there for 10 seconds, and then it barely managed to make a connection. But it's really difficult. It's not very reliable to do that. Like this one, I tried multiple times and couldn't get it to work. I got lucky on this connection. So like I said, that's why using something like a friction contact seems to be a better idea.
Did you use the solder iron included in the Easy Lab kit, or did you use your own solder iron?
I used the one in the kit.
Oh, I see.
Yeah. So there you go. So that is a little better contact there. I just got this guy again here. So it's making a nice contact with the copper, and that should actually register. So it doesn't have to be super great as a contact. So again, you might have to struggle with that. What I did is I just kind of very gently bent that inner conductor down a little bit. So that gave it a nice little pinch as well to get on there. So you might have to do a little bit of trial and error there, but once you get it to work, it doesn't have to be a perfect contact to get data off of your nano VNA. Let's see if I can do that. So I've got the VNA over here. Let's see, here's my VNA. I just need a cable. We'll go ahead and just plug this guy in. So overall, the lab works. This is really the only hard part, is getting that decent connection. So you can see this guy here. So you can see how it's got that characteristic circle for a length of transmission line. But if I can just get a decent connection, you'll see it suddenly change. So all I did was just kind of mash it on there, and you can record your data doing that. So I let it go, it goes back, and you see here, just getting that on there. Just get it, you kind of torque it a little bit to make contact, and you should get some decent data there. And again, using this might help you as well if you just kind of smush that in. Or if you're very brave, you can try to use the soldering iron and test your luck there. So that's going to be the only real challenge with this lab, I think. But we can go ahead and play around with some of the results here. So let's see, I'm going to go back and share my screen. Let's see, I'm going to open up the lab. I've got this here. There you go. So I created a script. It says process TDR lab 4. And we've got some MATLAB scripts that'll actually read the nano VNA for you. So have you seen these? I don't know if you've seen these. I'm pretty sure I uploaded them, but you need this nano open. So that establishes a connection with the COM port. And then this will read an array of all the frequency values that you've measured. And then this function here will then read all of the reflection coefficients. So all I'm going to do is plug this guy in here. So I'm going to start with my little 50 ohm strip just to kind of show you how it works. Let's see, I need to plug this into my laptop now. There we go. So I am plugged in. And while we're at it, let's go to our 1.5 gigahertz setting. There we go. So we're going to do that full sweep. So depending on your computer, you might have to figure out which COM port you're plugged into. It seems to always default to 3 on mine. And you just run this stuff. And you'll notice a lot of this, you should have written something similar when you did your code last week. The only major change is this zero padding thing that I talked about on Friday. So this is how we're artificially increasing the sampling frequency. I'm going to go ahead and run this. We'll see if it goes. There we go. So there's the reflection coefficient on a Smith chart. Or not exactly a Smith chart. It's the complex reflection coefficient that was measured by the VNA. Let's go through all the different plots here. So here is the time domain signal. And you can see that little sync function there. All you have to do is single out the little peak. And you can see it's about 1.86-ish nanoseconds, right? So let's do a quick little trial and error here. So this is what it looks like without the zero padding. You see how it's all garbled because the sampling is awful. And you can see also there's this uncertainty in where the heck is the peak, right? Because we have almost, how much is that? Almost a little over 3/4 of a nanosecond of uncertainty, which translates to multiple centimeters of uncertainty in the length. So but you can see it's just a very crudely sampled sync function. So when we do the zero pad, all it's going to do is essentially play connect the dots. It's also going to reduce the scale here. So you may have to do some normalization after the fact. So that's just a quirk of the FFT, that the magnitude of everything is going to be scaled by the number of points. So this peak is going to shrink. And I think there's a way to compensate for that, but I haven't actually done that. So you'll notice the data is fine. It's just going to change the scale a bit like that. So kind of cut it down by a factor of 5 there. But you see how it's nice and smooth now. And you can see it's a very clear sync function. So all we did was artificially increase our bandwidth by just stacking a bunch of zeros onto that reflection coefficient. And in fact, where's the polar plot? Oh no, I did the polar, I have a polar plot. So if you were actually do the plot after that, you would see the same twirl, and everything would suddenly shoot to 0 after that. But we're not plotting that data. So, but in any case, so you can see, we'll say about 1.86 nanoseconds, right? So I'll just say 1.86 e minus 9. That is my, my time. And now I can take a ruler and just measure the actual length of this thing. So if you look at my little desktop camera here, and you see it's about 15 centimeters in length. So we'll just say my total round trip distance is about 30. So my propagation velocity is distance over time, right? Which will then normalize to the speed of light. And you see it's about 0.54 c, which is a pretty accurate measurement, if you ask me. So that's kind of a cool way to now I can ask, okay, given that phase velocity, what is the effective dielectric constant of my board here, my transmission line? So F sub E, or sorry, we need to unnormalize our phase velocity first. Go back to the textbook. So the phase velocity is the speed of light divided by the square root of epsilon e. So that means my epsilon sub e is going to be the speed of light divided by the phase velocity, and then you have to square that. Like that. Although I have to not normalize by c. There we go. So that is implying 3.4. Right. That makes sense. So you notice the true dielectric constant is somewhere around like 4.2, and the effective dielectric constant is somewhere less than that. So what we can also do is, while we're at it, let's go ahead and plot the effective dielectric constant. So we already wrote our script here to return that epsilon e here. Okay, so we're calculating it using this expression right from the book. So let's do a quick little modification. I'm going to say something like this: z comma ee, that, and z naught of z, and then my effective dielectric constant is going to be that little guy there. So when you have multiple output arguments, I don't think you're allowed in MATLAB to say something like that. It won't like that. So you have to use these little dummy variables instead. So you notice I'm just creating an array of all zeros. Otherwise, it'll complain if it's dynamically adding to an array. So we just calculate it for a particular value. We store it into these little dummy variables, and then we stick it into the array when we're done. So now I'm going to plot my epsilon sub e like that. In fact, let's see. Yeah, there we go. So here is my, I have to change my axes first. So we'll say effective dielectric constant. We'll say epsilon sub e like that. There we go. So we found that the width was somewhere around here. What was it? Where was that? 3.2-ish gave us an effective dielectric constant. So we didn't quite calculate that. So what we'll have to do now is say, we got to do some basic calculations here. So this is going to be a little tricky, because I want to know what is the actual dielectric constant of this board here. So we're going to do another little sweep down here. So let's see, how do we do it? Because we know the width now. The width is fixed, but we don't know what the dielectric constant is. So I'm going to say something like this: length space of 4, 5. I'll do 101 samples, like so. I'm going to fix my width at 3.2 millimeters. So here we are. We're going to calculate true dielectric constant of microstrip board. So what we have to do now, let's see, I've got these values here, and I'm going to find the value of my true dielectric constant that gives me the measured effective value here. So I don't care about the impedance, I just care about, the effective dielectric constant, like so. So we'll do something like this. So I'm going to plot my effective dielectric constant as a function of the true dielectric constant. So remember, we measured the effective dielectric constant. We just need to single out on a graph which value of the true dielectric constant gave rise to it. So we're going to say true dielectric constant, epsilon r, and then effective dielectric constant, like so. So let's see. So here is the new graph. Ooh, it has a little singularity there on the bottom. Did I mess something up? Oh, that should be ER. There we go. That's better. Okay, so this is the curve we care about. So what I know is when I did my little measurement, I got an effective dielectric constant of 3.455. So I'm going to just go ahead and draw that onto the graph with a solid line. So we'll just say 4 to 5, and it was a value of 3.4550, something like that. So we run that again. Oops, sorry, I have to do a hold on command. Hold on, there you go. And what the heck? Oh, I did my axes backwards. So let's try that again. One more time, making little boo-boos. There we go. So that red bar is what we just measured. Because I knew the actual true length of the strip, that allowed me to calculate the propagation velocity, which told me the effective dielectric constant. And I knew the width, so I plugged that in. So you'll notice the true dielectric constant of my board is actually more like around 4.56. Okay, so the manufacturers will specify anything between 4.2 and 5 something. So you can see I have now just reverse engineered the dielectric constant of that material by simply saying, okay, here's the phase velocity going through it, and here are the equations. Sorry, so that was a little fast. I kind of went through that quickly. Are there any questions on that? Because that's essentially what you're going to be doing with your lab. You're going to be plugging into these boards here. You're going to characterize the impedance. You're going to figure out what the propagation velocity was, and then use that to kind of reverse engineer the dielectric constant. Like I said, that was a little bit fast how I kind of went through that. So are there any questions on that?
I don't have any questions, but at the same time, I did not follow.
That's
I lost you while I was trying to type code and look back and forth, so I apologize.
Yeah, that's okay. I went a little fast, but we still got another 5-ish minutes here. So we'll review exactly what just happened. So first things first, you're going to need a function that will return your characteristic impedance and your effective dielectric constant. So this is just the formula in the book, was this little function we wrote here. So you can see it's this guy. And if you like, I suppose I could post this online so that you can make use of that. Or at the very least, you can compare your code against this to make sure it's working. So then after that, we then asked, okay, how thick does my transmission line, or how thick does my strip have to be to give me 50 ohms? So you just create a plot of your characteristic impedance over width, and you see where it crosses 50 ohms. And you saw it came in right around 3.2 millimeters. I then built exactly that. I've got a little transmission line here in my microstrip that was about 3.2, and I just cut it by hand and laid it down. And then I did a measurement on it using the code that you made last week. So that was the TDR codes. Where are we at here? So this code here is basically, you should have something similar that you created last week. And you should be able to modify a bit if you want to read some of these functions here. But all we did was we did a measurement. Oop, I unplugged it. Let me plug that back in again. So we'll run that again. And you notice this was the TDR response. So the round trip time we found was about 1.8 nanoseconds. Given that information, I calculated the phase velocity in the transmission line. And then from that, I calculated the effective dielectric constant. So once I know the effective dielectric constant, I can then ask, okay, what is the true dielectric constant that gave rise to that value? So we did another plot here where I just did a scan through a bunch of possible dielectric constants. So, and I plotted the effective value as a function of the true value here. So I got a curve that looked like this. As I changed the true dielectric constant my effective dielectric constant followed this curve. And then I just picked out the value that seemed to coincide with my measurement. So it's just a little bit of matching graphs on top of graphs here. Oops, excuse me. So it was a few steps along the way, but you can see how just a little bit of information can tell you a lot about the physical parameters of a system here. So you see I just created an empty array of true dielectric constants. I put in the actual width of my transmission line, about 3.2 millimeters. And then we just calculated the effective dielectric constant at each value here. They're just little graphs and sweeps. And so this was the value I measured, which we use for the little curve intersections there. So it feels like a lot, but it should be pretty straightforward. But this is basically what you will be doing in your lab on Wednesday. And hopefully the most difficult part will be getting a connection on that strip. And then there'll be a little bit of code writing as well. So I'm thinking to at least help with that, we could upload this function here. This is actually the official one I wrote for myself. So I can make this available, and you can just kind of call this function to do the plots yourself. So while we're at it, I'm going to add another output argument for the effective dielectric constant here. There we go. Okay, so I will upload this to the website so you can make use of that here. It's just copying and pasting the equations from the book. So you can use this, and you won't have to spend too much time having to code that yourself. And I guess a question, have you used any of these new functions yet, or have you just been using that Nano VNA saver? Have you had a chance to try these guys out?
Just, I saw that you uploaded these codes to the Canvas page, but I haven't used them yet, no.
Okay.
Just the Nano VNA saver.
Yeah, I really like this because it sidesteps that stupid VNA saver program. It's a nice little program, but it's just clunky to me. I like to this just reads it immediately, and you don't have to deal with that extra unknown software. In fact, you can even look under the hood. So I documented it pretty well. And what it does is the Nano VNA just returns like character strings, and it has to unpack all of the character strings and turn them into numbers. But that's basically what, so there's a lot of weird serial port reading stuff here and a lot of bookkeeping involved, but it's pretty straightforward stuff.
Is it averaging the signal, or is it just one shot?
This right now is just one shot, and you saw it gave pretty decent results. I mean, there's not a whole lot of noise in it. It's not the noisiest thing, right? Nice smooth little curve. But if you're worried about noise, you could just run this thing, 10 times over and average the results. It would actually be pretty straightforward, right? You would just say something like, first you'd read the frequencies, then you'd create a gamma array, something like that. Then you would just say, I want to average it 20 times. You do something like this. So you'd say G, and then we'd say gamma is equal to gamma plus G over 20, like that. And that would average them out 20 times. So it's pretty straightforward to do averaging if you want. The one thing I'd really like to do is have it probe more of the frequencies. Because right now it'll only do 101 samples between your start and your stop frequency. It would be nice if you could have it like chop it up into sub blocks so you get better resolution in your output. But even so, it seems to work fairly well as is. So I'm not too much in a rush for that. But you can see if I run this, it'll just read 20 times. So it's reading, busy. Each one takes about a second to do the reading. So if you sit here for about 20 seconds, it'll probably finish it up.
So when you run the code, the frequency that it samples is the entire frequency of the maximum frequency bandwidth of the unit, or is it of the current CAL file that's being used?
It's from the current settings you have. So right now, that's a good question. Here, I'm going to unplug this. And if you
So
go
it's
to the, say what?
So what you're saying is you want to say have it do a 500 megahertz block at 201 samples, and then go from 500 to 1 gigahertz, get 201 samples, and then 1
Yeah.
gigahertz to what, and then put that together so you get a higher resolution.
Yeah, that would be very nice. I don't know exactly how to do that just yet. I know it can be done because I know Steve Blair kind of toyed with that. So right now, all it does is by default, sorry, it's giving weird results because it's calibrated for the cable here. So there we go. Let's do this again. So you see how it says start is 50 kilohertz, stop is 900. So it will automatically take 101 samples between those ranges. And if I recall my other setting, recall the number 4, it goes from 50 to 1.5 gigahertz. Again, it is just recalling these samples, or it's doing 101 samples between these limits. So that is what it does by default. What would be really neat is to say, chop it up into the 4 blocks. So the first block would be 1 to say 250 megahertz and do 101 samples, and then go 250 to 500 and do another 101 samples, and so on. Like I said, I know that can be done. Steve Blair put together some codes for that. I just haven't done that. And again, you don't necessarily need that resolution because, as you saw, you got pretty decent results from that TDR sweep anyway. But that's basically everything I've got for you today, and we're kind of out of time. So again, if you want to sit around or stick around and ask questions, you're welcome to. Otherwise, thank you for coming out. And I think I will upload that code because I don't want you to have to spend too much time beating your head on MATLAB codes in order to get this lab done.
I just want to double check. So is the exam on Wednesday or on Friday?
Friday.
Okay, cool, thanks.
And yeah, so I think I've got the idea. We went over that last week of which topics. So expect maybe one problem on the parallel plate waveguide, doing something like here are some mode amplitudes and calculating the power and the cutoff, that kind of thing. I might do another problem on either rectangular waveguides or the circular waveguide. So you might have to do some of that Bessel function stuff to calculate cutoff frequencies. And then one last problem on the microstrip, where I think it'll be something, I really like the idea of just doing a quarter wave transformer now that you've seen how to do all the mathematics of this. So you'll just have to pick out a width of the microstrip to give you the desired impedance, and then given the phase velocity, you'll have to figure out how long the strip will have to be to get your correct match, that sort of thing. So we've got at least one practice problem in the homework, and I'm thinking I'll just take that problem and kind of tweak the values a bit for a final bit. So that to me is a nice sort of engineering design kind of problem based on everything we've learned. Okay. So thank you for bearing with my sniffles and snorts. I've been really yucky for the last couple of days. But there you go. That's everything you need to know for your homework and for your lab this week.